I'm Vaibhav Gupta, currently a student of Computer Science and Engineering Department, IIT Bombay. I secured an AIR 54 in J 2009, and today I'll be teaching you some advanced level concepts of alternating current. In this module, we'll be solving a number of questions comprising different subtopics of alternating current, and at the end of the module, I hope that you understand all the questions pretty well, and I'll try my best to explain each and every question pretty well. And at the end of the module, you must be able to solve any question that can be framed from the topic alternating current pretty easily. So let's start this module with the first question, which is basically calculating the effective current, or you can say average current. So you have been given a function I equals to sine 2 sine 100 pi t plus 2 cos 100 pi t plus 30. 2 cos 100 pi t plus 30 degree. Now, you have been given this function of I, and you have been asked to calculate the effective value of current. So firstly, what do you mean by effective value of current? You must understand this properly. What is effective value of current? Effective value of current is basically the RMS value of the current. So this is the function of I given to you. You have to calculate the RMS value of this current. Now, as we studied in the basic module, we have a formula for calculating the RMS. I can write down IRMS, that is root mean square, to be T1 to T2, and you have to calculate RMS for a particular time, that is for one time interval. You calculate IRMS for a one time interval. So okay, since omega 1 and omega 2 are same, I can write this to be 0 to 2 pi by omega, where omega is 100 pi. So I can write down that you have to write I square dt upon. So this is one way of calculating the IRMS, wherein you write the function of I as a function of time, you square it, you average, take the average, and then after that you take the root of the whole thing. So this is the one method of calculating RMS, but we won't be doing it that way because that method is pretty long and is pretty tedious. It's a tedious job to do all the calculations and come to the final answer. What we'll be using is, we can say that this is given as I is equals to 2 sine 100 pi t plus 2 sine, can say 100 pi t plus 120 degree. So I can write down that 2 cos 100 pi t plus 30 degree can be written as 2 sine 100 pi t plus 120 degree. Now 2 sine 100 pi t plus 120 degree. So what I can do is, I can consider an I1, which is equals to 2 sine 100 pi t, and I can consider an I2, which would be 2 sine 100 pi t plus 120 degree. This would be my, you can say I2 equals to 2 sine 100 pi t plus 120 degree. Now, I can say that since this is my I1 equals to 2 sine 100 pi t and I2 equals to 2 sine 100 pi t plus 120 degree. Now, what I can write is, okay, I know that I is equals to I1 plus I2. Let's remove this formula because we don't need it. Now what we'll use, as I told you in the basic module, that phasor, the technique of writing phasor for the sinusoidal functions is pretty useful in solving questions easily. So we'll apply the same technique. We'll write down the phasor of I1. So phasor of I1 can be written as like this, where I1 maximum you can see is 2. Now, if I want to write I2, the phasor of I2 is sine 100 pi t plus 120 degree. So that phasor would be here at an angle 120 degree, and it has a value 2. So if I want to write total, that is I equals to I1 plus I2, that is this plus this. So I can write down the result to be root over 2 square plus 2 square plus 2 into 2 into 2 into cos 120 degree, where cos 120 degree is minus half. So I can say this gets cancelled out. So this would come out to be minus 4, and if this comes out to be minus 4, this can be cancelled out, and thus I comes out to be 2, where this I is the maximum value. So I maximum comes out to be 2. That is the maximum value of this quantity comes out to be 2. Okay. So if the maximum value comes out to be 2, we can say that IRMS has to be equals to 2 upon root 2, which is equals to root 2. Okay. Now think for a second that can we say that IRMS for a time period is I maximum upon root 2. We derived this formula in the basic level, and I hope you remember it, that the root mean square value for any sinusoidal function is equals to maximum value upon root 2. But can I say that this I, that is I1 plus I2, is a sinusoidal function? Firstly, if you remember the concepts of SHM, then you can easily say that yes, I1 plus I2 will give me a sinusoidal function only, because this is a harmonic sum of two sinusoidal functions. So the result will definitely come out to be a sinusoidal function. But let me again remind you. Okay, you got I1 plus I2. So this is your I1, this is your I2. What happens is, if you calculate I1 plus I2, okay, so if you calculate I1 plus I2, you'll get a result something like this, which would be IM, which I calculated as 2. So this would be equals to 2, and I believe, since because of symmetry, I can say that this angle would be 60 degree, but it need not be necessarily. So if this IM is 2, so I can write down the function, I can easily write down this I function now, because I know I is, the maximum value is 2, and it is a phasor, and it is at a 60 degree. I can say 2 sine 100 pi t plus 60 degree. This would be the I function, which we will get by IM plus I2. And if you want, I can derive this function also for you. Okay. What we'll be doing is, for deriving this function, means I did this calculation from the phasor diagram. Now let's do it mathematically. I can write it down as 2, and in the bracket I can say sine 100 pi t plus sine 100 pi t plus 60 degree. So I can say I equals to 2, and I can say sine A, I have to write down the formula of sine A plus sine B. So what is the formula of sine A plus sine B? Let's find it out. I can say, okay. Oh, sorry, here it is 120 degree, right? It is 120 degree. If I want to write down the formula for sine A plus sine B, I can write it down as, okay, I know that, okay, let's handle some trigonometry somewhere. Okay, now I did the phasor term, now I am doing it mathematically. So let's handle some mathematical terms. I can say sine A plus B is equals to sine A sine B sine A cos B plus cos A sine B, and I can say sine A minus B to be equals to sine A cos B minus cos A sine B. Now if I add these two terms, I'll get sine A plus B plus sine A minus B is equals to sine A 2 sine A cos B. Now I can say, let A plus B equals to C and A minus B equals to D. I can say that A is equals to C plus D by 2 and B is equals to C minus D by 2. So I can say that sine C plus sine D is equals to 2 sine C plus D by 2 into cos C minus D by 2. So using this trigonometric formula, I can say that I is equals to 2 sine A plus sine B is given, that is sine C plus sine D. So I can write this down as 2 sine C plus D by 2, that is this plus this by 2, which would be 100 pi t plus 60 degree, because it would be 100 pi t plus 100 pi t plus 120 upon 2, so 100 pi t plus 60 degree into cos C minus D, that is cos of minus 120 degree. Cos of minus 120 degree. And cos of minus 120 degree will come out to be minus 2, cos of minus 120 degree. Okay, sorry, not cos of minus 120 degree, cos of minus 60 degree, because it is C minus D by 2. So 100 pi t minus 100 pi t plus 120 degree divided by 2 would be cos of minus 60, and cos of minus 60, as you all know, will come out to be 1 by 2. So 1 by 2 gets cancelled out with this 2, and finally you get what result I derived from the phasor diagram. So you now can see what is the strength of the phasor diagram. If you understand the concept of phasor diagram clearly, then there is no need to do all this mathematical calculation, and you can reach the final answer just by having a look at the phasor diagram. Now let's after solving this first question, let's move on to the second question of this module. Question number 2 says that an alternating current E sine over 100 t volt. This is the EMF given, and through an AC emitter. Okay. So this EMF is connected through an emitter to a capacitor, and capacitor, the capacitance of the capacitor is given to be 1 microfarad. AC, what would be the reading of the emitter? Now, the question asked is that what will be the reading of this emitter. So firstly, let's understand what an emitter, or what the various instruments, that is the voltmeter, the emitter, and what do they read actually. So the voltmeter reads the RMS voltage across it, and the emitter reads the RMS value of the current which passes through it. So all the instruments actually measure the RMS value of whatever they are assigned to measure. So what we have to find out in this question is what is the value of RMS, IRMS. So we know from the formula we can directly say that Im is equals to Vm upon Xc. Vm is given to be 200 root 2 upon Xc, which would be 1 by omega c. So 200 root 2 into omega, which would be 100 into c, which is 10 to the power minus 6 farad, and this would be the value of Im, which would be, I think, 2 root 2 into 10 to the power minus 2. And if I want to calculate IRMS, it would come out to be 2 into 10 to the power minus 2, that is 0.02 ampere. So the emitter would read 0.02 ampere, or you can say 20 milliampere of current. So important point to be noted is that the various instruments that we generally use measure the RMS value of current or voltage, whatever they are assigned to measure. Now let's move on to question number 3. Question number 3 is an AC source producing EMF. Okay, you have a AC source which produces EMF. V is equals to V naught cos 100 pi t plus cos 500 pi t. I think it is, yeah, cos 500 pi t. Okay. Now, okay, this alternating source of current is connected to a capacitor and a resistor, and the current found is I1 into cos 100 pi t plus phi 1 plus I2 cos 500 pi t plus phi 2. So these are the two values of current found. Means this is the value of the current, instantaneous value of the current, and this is the instantaneous value of the voltage. Now there are some options. Is I1 is less than I2, B I1 is greater than I2, C I1 is equal to I2, and D is you cannot find now. You cannot find. So what are the answers of this question? What is the answer of this question? Now if you have a close look upon this question, you can say that V is basically a harmonic sum of two sinusoidal voltages V1 and V2. So if I solve every individual voltage, that is if I solve for V1 this circuit, I'll get this part, and for V2 I'll get this part. Because they both have different omega, I1, that is the maximum value, will differ, because we know that Im is equals to Vm divided by Z, and for a RC circuit Z depends on the value of omega, because we know that Z is equals to root over R square plus XC square, that is root over R square plus 1 upon omega square C square. So in the calculation of Z, omega is involved, and since omega is different for V1 and V2, there would be two different currents, and you will have I1 and I2 as different. So the question asked is which means what is the inequality between I1 and I2. So if I write, I can say Im can be written as Vm upon root over R square plus XC square for a RC circuit. So this is equals to V upon root over R square plus 1 upon omega square C square. So I can see that if omega is greater than if omega means, I say that if omega, we can say that omega 1 is less than omega 2. So let's say I denote this as this is equals to Z. So if omega 1 is less than omega 2, I can see that since this denominator is less, I can see that Z1 has to be greater than Z2, since omega 1 is less than omega 2. And if Z1 is greater than omega Z2, I can say that I1 has to be less than I2. And since I1 is less than I2, our answer to this question would be A. So you can see this question was pretty simple if we remember the formulas and understand if you have a AC source as a harmonic sum of sinusoidal voltages, then you will get two different values of current if the circuit has, you can say RC or RL circuit, where omega is involved in the calculation of impedance. So this was our question number 3. Now let's move on to question number 4. Question number 4 says that in an RC circuit you have been given, okay, there is a RC circuit, some quantities are given. The RMS voltage of the source is 200, VRMS is given as 200 volt, and omega is given as 50 hertz. Sorry, omega is not given as 50 hertz. Remember, frequency is given as 50 hertz. So omega you have to find out. So omega is found out as omega, that is the angular frequency, is basically 2 pi divided by f. This is the value for the omega, that is 2 pi divided by f. Now it is given that R is equals to 100 and C is equals to 100 upon pi. R is equals to 100 ohm and C is equals to 100 upon pi microfarad. And is there anything else given? Okay, this formula, omega is basically the angular frequency is 2 pi into f, because you have to multiply 2 pi by f, that is 2 pi the radians, which you have studied in the SHM. So omega is 2 pi f, this is the value of R, this is the value of capacitance. Now a few things are asked. Let's note down what all things are asked. You have been asked the impedance, you have been asked the power factor angle generated by PF, power factor, and you can say, okay, there is a whole list of things which can be derived. Now let's derive each and everything which is associated with an RC circuit. Firstly, V maximum, Simply 200 root 2. Okay. Now let's do the calculation for I. Firstly, let's calculate the impedance. Impedance is equals to root over r square plus 1 by omega square c square. 100 square plus 1 upon omega, that is 2 pi, that can be written as 4 pi square into 50 square into 100 square upon pi square. So 450 this can be taken as omega 1 upon omega c. So this can be written as root over 100 whole square plus 1 upon 250 100 whole to the power 4. Am I correct? Means I don't think this is the value. Xc square, I think, yeah. I think I made a mistake somewhere. 1 upon omega c 100 square 1 upon omega square c square. So you get, okay, yeah, one thing I forgot. This is microfarad. So you, what do you put in here is, firstly let's do, let's calculate xc. xc, which comes out to be 1 by omega c, which is 1 by 2 pi into 50 into 100 by pi into 10 to the power 6. So I can say pi gets cancelled out, and 100 10 to the power 4. So this comes out to be 100. So xc comes out to be 100. So impedance, that is z equals to root over r square plus xc square equals to root over 100 square plus 100 square, that would be 100 root 2. The unit of impedance can be guessed as 100 root 2 ohm. Now, impedance, now I got impedance, so we can easily find out what would be the maximum current. Maximum current would be 200 root 2 upon impedance, that is 100 root 2, which would be 2 ampere, and thus I can guess the value of IRMS, which would be root 2 ampere. So I got the maximum current, I got the impedance, I got the RMS. Now let's calculate the power factor angle. Power factor angle, we remember from the basic module that power factor angle is given by the formula tan phi equals to xc upon r. So tan phi xc we calculate as 100 upon 100, so this is 1. So phi comes out to be 45 degree or pi by 4. So power factor angle comes out to be 45 degree. Now power factor, that is cos phi, comes out to be 1 by root 2. So this is our power factor. What is the average power? Average power is VRMS into IRMS cos phi, and thus we know that VRMS is 200, so it can be 200 into IRMS root 2 into cos phi, which is 1 by root 2. So average power is basically 200 watt. So we calculated average power, we calculated power factor, we calculated power factor angle, IRMS, I maximum, V maximum is something left. Okay, it says maximum voltage across R and maximum voltage across C. So if you want to calculate maximum voltage across R, we can say VR, that is VR maximum would be I maximum into R. So I maximum we got as 2 ampere, so 2 into 200, so 200 volt would be the value of VR maximum. If you want to calculate VC maximum, it would be IM into XC. XC is again 100 volt, so it would be 200 volt. So VRM and VCM are 200 volt and 200 volt respectively. So okay, so maximum voltage across R, maximum voltage across C. Okay. So these are the basic calculation, and I don't think I have left anything. Okay, it says the value of current. The value of current can be directly written as 2 into sine, what was given, omega. Omega came out to be 100 pi. So 100 pi t plus pi by 4. So this would be the current as a function of time. So I think these are the basic calculations which we can solve for the value for an RC circuit. So this was our question number 4. Now let's move on to question number 5. Question number 5 says that there is a bulb along with the inductor, and you have a AC source. Here you can say you have a bulb which acts as a resistance, and herein you have a inductor like this. The question says a bulb is rated at 100 volt and 100 watt. So bulb here, the resistance is 100 volt and rated as 100 volt and 100 watt. It can be find out the inductance of an inductor that should be connected in series with the bulb to operate the bulb at its rated power. Okay, so this is an AC source of 200 volt and 50 hertz. This is the basic definition of the 200 you can say, okay, this is actually a practical examples of what happens in what happens in our daily routine. You get a 220 volt 50 hertz supply at your house, where 220 volt is the maximum value. The RMS value comes out to be near about 200 volt. So that is the amount of that is the AC current, that AC voltage you get at your houses. Now let's say you have a bulb which is marked at 100 volt and at 100 watt. So you can calculate the resistance of such a bulb. It would be 100 square upon 100, that would be 100 ohm. V square upon W, we know that V square upon R is the power, so I can say that V square upon W, that is 100 ohm, is the resistance of this bulb. So if 100 ohm is the resistance of this bulb, I can say that, okay, 100 ohm is the resistance of this bulb. So you all may have, if you all have a bulb or maybe a tube light in houses which has such marking, that is 100 volt and 100 watt. What happens is there is a choke coil. Many of you may have seen in the case of tube light, there is a choke coil associated with a tube light. That choke coil is nothing but an inductor. Inductor or choke coil. And that choke coil is used so that you had a 220 volt potential here. So you get only a 100 volt potential at this point, and thus that choke coil is used. So I can say that what asked is that you have to calculate the inductance such that 100 volt is applied across this 100 volt is applied across this bulb. So we can see that the resistance is 100 ohms. So I can say that IRMS is equals to VRMS upon Z. So IRMS, what we have to find out is, okay, now you can see that since R is 100 here, what current should pass through this resistor? Since R is this, so I can say I must be 100 volt upon 100 ohm. That is, if 100 volt is applied across this resistance, 100 ampere is its resistance, then current passing through resistor must be 1 ampere. That means RMS, the root mean square current through this resistor, must be 1 ampere, so that it emits 100 watt power and not more than that. That means IRMS is 1 ampere. So this is 1 equals to VRMS, which is 200 volt upon Z. So Z comes out to be 200 ohm. So which has to be equals to root over R square plus omega square L square. So I can say 200 square is equals to this. R square is 100 square. So I can say 300 into 100 is equals to omega square, which would be 4 pi square, omega, let it be omega square L square. So L can be taken as 100 root 3 by omega, which would be 2 pi into 50, and thus comes out to be root 3 by pi. So inductance of this inductor comes out to be root 3 by pi. Okay. So you can clearly see that this is the practical example what you see in your daily life. This inductor is basically the choke coil, or maybe if you're not seen in a tube light, just look at the base of the tube light. You will find at the center grayish humped part, and that is the choke coil. You may find maybe some markings on it written inductor and maybe its inductance also if you look at it closely. So this is our question number 5, which is based on the practical application of AC current in your houses. Now, after doing question number 5, let's move on to question number 6. Okay, question number 6 is a question from which comprises the resistance, the R, L, and C. That is, this question is from the RLC circuit. Okay, there is a circuit shown like this, and you have a inductor here, you have a resistor here and a capacitor. Inductor, this is going to be 200 volt 50 hertz. Inductor is given to be 2 by pi Henry and 100 ohm and 100 by pi microfarad. These are the values, and you have to calculate the potential across L, across C, across R, across C, and everything related to this circuit. These things are given. So let's start calculating everything. Firstly, let's calculate the impedance of the circuit. Whenever you get a circuit of AC, whenever you get a question comprising an AC circuit, maybe R, maybe L, or any combination of that, firstly calculate the impedance of the circuit. So let's calculate the Z, that is the impedance. Z would be root over R square plus XL minus XC whole square. So R we already know. Let's calculate XL, which is omega L, which would be 2 pi into 50 into L, which is 2 by pi. So this would be 200 ohm, and XC would be 1 by omega C by 2 pi into 50 into 100 divided by microfarad. This would be 10 to the power 6, so this would be 100 by pi. So this divided by pi gets cancelled out between 100. So this would come out to be 100 ohm. So XL comes out to be 200 ohm and XC comes out to be 100 ohm. So if I want to calculate Z, I'll get Z equals to root over 100 square plus 100 square, which would be 100 root 2. So this is the value of the impedance. Now after getting the value of the impedance, I can write down that IRMS is equals to VRMS, that is 200 upon 100 root 2, which would be root 2 ampere. And if IRMS is root 2 ampere, I can say I maximum has to be 2 ampere, because I maximum is root 2 times IRMS. So I maximum comes out to be root 2 ampere. Now I know from the formula, if I want to write the power factor angle, I can write down tan phi equals to XL minus XC upon R, which would be 200 minus 100, that is 100 upon 100, which would be 1. So I'll get power factor angle to be pi by 4 and cos phi power factor to be 1 by root 2. So now I have power factor angle, IRMS, VRMS. So if I want to calculate the average power would come out to be VRMS, that is 200 into IRMS, that is root 2 into cos theta, it is root 2. So it would be 200 watt. So this is the value of IRMS. Now we want to calculate the potential difference across L, R and C. So let's calculate what would be the value of VL. For calculating that, we need the instantaneous current. So let's calculate instantaneous current first. So we know that phi is equals to pi by 4. So I can write instantaneous current to be I maximum, that is 2 times sine 100 pi t 100 pi t plus pi by 4. So since V is equals to So I is equals to 2 sine 100 pi t plus pi by 4. So this is the formula for the instantaneous current, 2 sine 100 pi by t plus pi by 4, because the power factor angle, that is the phase angle between I and V, is this. So this is the value of I. Now if I want to calculate VL, I can write down VL to be, that is potential difference across inductor, can be written to be the instantaneous current, means I can say I maximum, which would be 2 into XL, that is 200 ohm, into sine 100 pi t plus pi by 4 is this angle, and I can say, I know that in an inductor current lags behind the capacitor, and thus potential difference leads the current by an angle of pi by 2. So I can say this plus pi by 2. So this would come out to be 400 sine of 100 pi t plus pi by 2 plus pi by 4 would be 3 pi by 4. So this would be the value of VL. And if I, okay, let's remove the impedance calculation. Remember, Z is equals to 200, 100. Now, if I want to write down the VR, that is the instantaneous potential difference across the resistance R, I can say that it would be I into 100, and it would have the same phase angle, so it would be 100 pi t plus pi by 4. This can be written as 200. And if you want to write VC, I can say 2 into XC, that is 100 into sine 100 pi t plus pi by 4. Now, we know that in capacitor, current leads the voltage by pi by 2. That means potential lags behind the current by pi by 2. So this can be written as 2 into 100 sine 100 pi t plus pi by 4 minus pi by 2. And thus it can be written, VC can be written as 200 sine 100 pi t minus pi by 4. So this is the value of instantaneous capacitor, instantaneous voltage across capacitance. This is instantaneous voltage across resistance. This is instantaneous voltage across L. Now, sometimes they may ask that what is the value of instantaneous voltage across the combination of L and R. So if you want to calculate the instantaneous voltage at the you can say at the combination of L and R, what you do is you have the value VL, you have the value VR, you add them, and what you do is you use the phasor diagram. You know that, let's say this is VR, this is VL. So you calculate the maximum. The VL maximum is 400 and VR maximum is 200. So you calculate, and you can say theta to be 400 upon 200, which would be 2. Am I correct? Yeah. So theta comes out to be tan inverse of 2. So here would be your VLR, let's say. So VLR can be written as firstly V maximum square plus VL square plus VR square whole over root. That is root over 400 square plus 200 square. That would be, I believe, 200 into root 5. So it come out to be, so VLR can be written as 200 root 5, and sine over, we have 100 pi by 2 plus pi by 4 as VR. So this would be 100 pi t plus pi by 4 plus tan inverse of 2. So this would be the value of the potential difference across the LR component. Now, this is the instantaneous value of potential difference across the LR component. Similarly, if you want to find out the potential difference across LC component, what you can do is, okay, what should I remove now? Okay, I can remove the XC calculations. I just write down the answer. XC came out to be 100 ohm, XL came out to be 200 ohm, and IRMS I can remove, IXM I can remove, and I can remove this calculation. Yeah. Now Now you can see that if I want to calculate the capacity, the potential difference between these 2 points, that is R and that is between R and C, I can write down that VR is here and VC is here. So you can say VC is 200, VR is 200. So I can say tan xi, let's say, is equals to 200 upon 200. That would come out to be 1, and thus xi comes out to be pi by 4. So I can say that the VCR would be forming an angle of pi by 4 in the negative direction, and if I want to calculate the value of VCR maximum, it would be root over, you can say 200 square plus 200 square, that would come out to be 200 root 2. Yes, it would come out to be 200 root 2, and thus I can say that VCR can be written as 200 root 2, 200 root 2 sine over 100 pi t plus pi by 4 minus pi by 4, and thus this would be the value of VCR, that is 200 root 2 sine 100 pi t. So this is the way how do we calculate the various potential difference across each component and maybe a pair of component. So I believe that from this question you got means this was the maximum hardest question that can come from the topic alternating current when you have a RLC circuit and you have. So keep in mind always that whenever you have such circuits, always remember that phasor diagram is, I believe, the most helpful tool that you have in your hand. Now, this was question number 6. Now, let's move on to question number 7. Okay. Question number 7 is again, okay, now we have solved some easy questions. Now, let's restart from the topic where we started. Okay. So first question is, you have to calculate the RMS value of current again, wherein current is given to be 3 plus 4 sine omega t plus pi by 3. 3 plus 4 sine omega t plus pi by 3. 3 plus 4 sine omega t plus pi by 3. You have to calculate the, what you can say, you have to calculate the RMS value of this quantity. Now, how do we calculate the RMS value of this, wherein you don't have a harmonic combination? Means we did a question which had harmonic sum of 2 sinusoidal functions, so we guessed that okay, the final answer would be a sinusoidal function. But for this quantity we cannot use the basic laws which we did. So how do we calculate the RMS value for this quantity? So what we do is, in this question we use the basic law for calculating the RMS that we know, and that is IRMS is given by 0 to 2 pi by omega 3 plus 4 sine omega t plus pi by 3 whole square dt. So I can write this down as, and it's root over the whole thing. So you have to calculate this quantity. Now, yeah. So this can be written as root over 9 into integral of 0 to 2 pi by omega dt. Or if I break it down, I can say, okay, herein you will have this component and it would be divided by 0 to 2 pi by omega dt. So these two things get cancelled out and you will have a 9, just a 9, plus you will have a 24 sine omega t plus pi by 3. Whose integral has to be taken from 0 to 2 pi by omega upon 0 to 2 pi by omega dt, and plus you will have a 4 4 Now, looking at this question, looking at this equation, it would be pretty foolish to solve each and everything by the method we know. So, firstly, remember from the basic module we studied that average or the mean of a sine function over one time interval is 0. So, this is the sine function and its average is taken from 0 to 2 pi by omega, that is one time period of this function. So, this would come out to be 0 for sure. What about this quantity? This quantity, let's say if I take a current I equals to 4 sine omega t plus pi by 3. Let's say I take a quantity like this. So isn't this quantity written as IRMS square? Because what IRMS would be, capital IRMS, root over this whole thing square, 0 to 2 pi by omega dt upon 0 to 2 pi by omega dt. So this can be written as IRMS square. So I can write this down as small IRMS to be equals to 9 plus IRMS square, where IRMS is the IRMS of capital I. So I can write down IRMS equals to root over 9 plus, now we know that IRMS of this sinusoidal curve would be 4 by root 2. So you have to square that. So you will get 16 by 2, which would be 8. So this would be equals to root over. So IRMS for this quantity would come out, IRMS of this function would come out to be root 17 ampere. So in this question we saw that whenever you need to calculate the RMS value, you just need not start doing it mathematically, just think of it and you can maybe just break it down to some RMS values which you already know. So this was our question number 7. Now let's move on to question number 8. Question number 8. Question number 8 is you have E equals to E1 sin omega t plus E1 cos omega t. Then you have to calculate the ERMS. Again, calculation of RMS. Again, we will not go into, you can say, we will not go into the tough calculations. We will just use our mind and use some tricks and find out the answer quickly. So we can write this down as E1 sin omega t plus E2. Sorry, this is E2, I believe. Yeah, this is E2. E2 sin omega t plus pi by 2. So this is the value of E. Now, if I want to draw the phasor, I can again draw phasor E1 like this and E2 like this. So the resultant summation of them would come out to be somewhat here. That would be E, that would be our E, and E, the E maximum can be written as root over E1 square plus E2 square, and thus ERMS, that would be E by that, and thus the relation between ERMS would be similar, that is ERMS would be equals to root over E1 square, if this is the relation between E equals to root E1 square plus E2 square, if you want to calculate ERMS, that would be E by root 2, and that would be root over E1 square plus E2 square upon 2. So this would be the answer of the calculation for ERMS. So we can see that phasor diagram is pretty useful in this calculation also. So this was our question number 8. Now let's move on to question number 9. Question number 9 says that 1000 watt. There is a lamp of, or you can say a group of lamp of 1000 watt power, marked as 1000 watt power. It's and there is an AC voltage applied to it, which is 200 sine 310t plus 60. So you have to calculate the RMS current through this. You have to tell us the value of what is the RMS current through this, through the lamps. So firstly, understand that LEMS can be considered as a resistor. So if we know that for a resistor, power factor, that is cos phi, is 1 because the power factor angle is 0. So the average power is equals to 1000 watt, can be given as VRMS by root 2 into IRMS by root 2, which is equals to VRMS by root 2. Sorry, this was VRMS into IRMS. So power that is equals to V maximum, that is 200 upon root 2 into IRMS. IRMS is IRMS, and thus IRMS can be written as 5 root 2 ampere. So we get IRMS to be equals to 5 root 2 ampere. Now this question was pretty simple, but the reason I took this question is that sometimes what people do is, since this is the equals to 200 sin 310 t plus 60, what sometimes they do is they take the power factor angle to be this 60 degree, considering that I can be taken as, let's say, I maximum into sine, let's say, 300t. So what they think that this is the value of, this is the equation of I, and thus they confuse the power factor angle with 60 degree. But that is not the case. Since the circuit is purely resistive, the power factor angle has to be equals to 0 degree. So remember that point, that in a purely resistive circuit, power factor angle is always equals to 0 degree. Now let's move on to question number 10. Question number 10 is an objective question, and it is asked that energy dissipates in an LCR circuit. We all have studied the LCR or RLC circuit. The question is that energy in an LCR circuit dissipates in, and the options are L only, C only, R only, or all the three, that is in L, C and R, all three of them. So the answer to this question is that the energy in an LCR circuit dissipates only in R. The reason being, we all have studied that in a purely capacitive circuit there is no dissipation of energy, and the average power consumed by a purely capacitive circuit is 0. And similarly, average power consumed by a purely inductive circuit is also 0. So what happens in a RLC circuit is that whenever energy is given by the AC source, some of it is stored in capacitance, some of it is stored in inductance, and some of it dissipates as a heat energy in the resistance. So in case of capacitance and in case of inductance, energy is not dissipated, energy is stored in capacitance and energy is stored in inductance. But in resistance, energy dissipates as heat energy. So in an LCR circuit, energy only dissipates in resistance. So this was our question number 10, basically objective question, just to tell you some theory. Question number 11 says that in an AC circuit, the instantaneous current is 0 when the instantaneous voltage is maximum. Okay, so the question says that instantaneous current is 0 when instantaneous voltage is maximum. So it says that what maybe the circuit be. So let's understand, if instantaneous current is 0 when instantaneous voltage is maximum. So let's say if this was our voltage, it says that at when instantaneous voltage is maximum, the current is 0. So it can be like this. It can be like this. So you can see that you can see that there is a phase difference of pi by 2 in the equation of the voltage and the current. So if the phase difference between the voltage and the current is pi by 2, then the circuit can be an inductor circuit, circuit can be a capacitor circuit, circuit cannot be a purely resistive circuit, or circuit cannot be a RC circuit, circuit cannot be a RL circuit. Circuit can be purely capacitive, purely inductive, LC circuit, or it may be RLC circuit also, because in RLC circuit also sometimes I made a mistake. In an RLC circuit also it is not possible. In an LC circuit it may be possible, but in an RLC circuit this is not possible. So the circuit may be L, circuit may be C, or circuit may be LC. So in these three cases this can happen. Now the next question is, in a series LCR circuit the voltage across R and okay, This is a pretty good question. Sometimes this is our question number 12, and sometimes students get confused in such things that you can see that. Okay, in a RLC circuit, this really is a good question in respect that many students get confused here. So this is a LCR circuit or RLC circuit. If instantaneous, mind it, if instantaneous voltage of AC source is V, instantaneous voltage is VR, VC and VL, then what is the relation between all these four quantities? The relation between instantaneous voltages is V is equals to VR plus VC plus VL. This comes from the Kirchhoff's voltage law. That is, if in this loop at any instant I apply KVL, then V has to be equals to VR plus VC plus VL. But let's say if this is VRMS, RMS voltage of this, and this is VRRMS, VCRMS and VLRMS. What is the relation between these four quantities, that is VRMS, VRRMS, VCRMS and VLRMS? The relation between them is VRMS square is equals to VRRMS square plus VCRMS square plus VLRMS square, and similar is the relation between V maximum, that is VM square is equals to VRM square plus VCM square plus VLM square. So this is really a great point of confusion between students, that is the instantaneous voltages is V equals to VR plus VC plus VL. But RMS, for RMS we have a condition VRMS square plus VRMS this, and for maximum also we have this equation. So this is correct and this is correct, and do not get confused between these two things. Okay, so remember this thing. So this was our question number 12. Question number 13 says that an AC voltage of V equals to, okay, this is not basically solving. So V equals to 220 root 2 sine omega t plus pi by 2 will be read by a DC voltmeter. So this question is basically to tell you what does a DC voltmeter read. A DC voltmeter reads the RMS value of the AC current. That is, whatever is the RMS value of the AC current is read by the DC voltmeter as a constant value. So since the equation of this AC voltage is given as 220 root 2 sine omega t plus pi by 2, you can see that V maximum is 220 root 2, and thus the DC voltmeter will read the RMS value, and that would be 220 root 2 upon root 2, and that would be 220 volts. So this would be the value read by a DC voltmeter. Now let's this is a good question. Let's solve question number 14. Question number 14 says that there is a circuit given, and you have here you have a bulb, here you have an inductor, and again here you have a bulb, and here you have a AC source. AC source is 220 volt 50 hertz, and values are given some 10 millihenry and 500 microfarad. So this is, and bulbs are V1 and V2. So this is the value given, and it is said that V1 and V2 are identical. Now the question asked is, which one will glow brighter? So the bulb which consumes more power will glow brighter, that is for sure. Okay, so we have to calculate which bulb will glow brighter. So the bulb which consumes more power will glow brighter. So you have to calculate which bulb consumes more power. So we know that in these two circuits are parallel to each other. In this circuit, there is an inductor attached. In this circuit, there is a capacitor attached and a resistor. This is acting as a resistor. We know that in a RC circuit or in a RL circuit, all the power is consumed by the resistance. So there is no power consumed by the capacitor or by the inductor. So all the power that would be consumed by this parallel branch would be consumed by B1, and all the power that is consumed by B2, this branch would be consumed in B2. So effectively we have to calculate which branch will consume more power. So okay, now we know that the voltage, that is V across both these branches, is same. That means the branch which will consume more current, that is the branch which will does that mean that the branch which consumes more current will have the more will consume more power? No, because you know that average power formula is VRMS IRMS cos phi. So maybe one of the branches may consume more current, but the cos phi factor for two branches would be different, and thus the answer may come out to be reversed. So let's check this out. We know the average power formula to be equals to VRMS IRMS cos phi. So we know that VRMS for both the branches is same. So we have to calculate IRMS cos phi. So for that, let's calculate the impedance of these two circuits. Let's consider this as branch 1, this is branch 2. So Z1 is root over R square plus XC square, and Z2 is root over R square. Since the two bulbs are identical, R1 and R2 are equal, R2 plus XL square. Let's calculate XC and XL. XC is 1 by omega C, which is 1 upon omega is 2 pi 50 hertz into, is this really 500 microfarad? Yeah, it is 500 microfarad. Now we have 500 and microfarad, so 10 to the power minus 6. Now we can say that this is equals to 10 to the power 6 divided by 5 into pi into 10 to the power 4. And 10 to the power 4, so this would become 100 upon this, and this would become 20 by pi ohm, and XL would be omega L, which would be 2 pi into 50 into L, which would be 10 millihenry, so 10 upon 1000. So this would come out to be pi ohm. Seems pretty bad data, but okay, whatever. Seems to be a pretty bad data, but okay, whatever. So this comes out to be pi ohm, and this comes out to be 20 by pi. That would be nearly, you can say 6 point something something something, and this is 3 point something something. So if we compare, we can say that XC is greater than XL. That means Z1 is greater than Z2. Z1 is given to be greater than Z2, and if Z1 is greater than Z2, I know that IRMS is equals to VRMS upon what? Z1. So I can say IRMS 1 is less than IRMS 2. So this is the relation between the IRMS in both the circuits. Now what is the relation of cos phi? Now since we know that XC is greater than XL, we know that in is XC upon R, or it is XL upon R for an inductive circuit. Since XC is greater than XL, that means tan phi 1 is greater than tan phi 2, which would imply that phi 1 is greater than phi 2, and which would imply that we are considering phi to be between 0 to pi by 2, and thus if phi 1 is greater than phi 2, then cos phi 1 is less than cos phi 2. Now from this we can say that since IRMS 1 is less than IRMS 2 and cos phi 1 is also less than cos phi 2, we can say that this whole quantity, that is power consumed by the bulb 1, that is P1, would be less than average power consumed by the bulb P2. Means it's okay, let's not write this way. Okay, let's write it average power like this and average power by P2 like this. So we can say that average power consumed by the bulb 1 is less than average power consumed by the bulb 2, and thus B2 will glow brighter than B1. So you can see this was a pretty good question, means it was a question away from the league of questions which are asked from the chapter alternating current. Now let's move on to question number 15. Move on to question number 15. Okay. Question number 15 says that if a direct current, okay, you have a direct current of magnitude A and it is superimposed over a B sine omega t, and then through a wire, that is effective value of resulting current. Now you have to calculate the RMS value. So current A, so the final current would, since it is superimposed, it would come out to be A plus B sine omega t. This would be the final formula for the after the superimposition. So if I is equals to A plus B sine omega t, I can write this down as, so if I want to calculate the RMS value, I can write it down as the time period of this function will be same, so it would be this would be the formula for the calculation of IRMS. So I can write this down as okay. Sine omega t square. So I can write this down as 2 pi by omega. So in this way, I can write this down as like this. So I can write this down as root over A square can be taken out because it is constant. So I can write this down as A square and integral 0 to 2 pi by omega dt, and that can be written as into 2 pi by omega, and in the denominator I'll have 2 pi by omega plus 2ab integral 0 to 2 pi by omega, I'll have a 2 pi by omega sine omega t dt plus 2 pi by omega p sine omega t whole square dt upon integral 0 to 2 pi by omega dt. So this is the formula which we'll get. Write it down like this, and thus now see this can get cancelled out. Now see some tricks. Okay, we know that sine omega t is a periodic function and its period is 2 pi by omega, and we know that the average value of sine omega t over one period of it is 0. So we can directly say that this part of the formula comes out to be 0. What about this part? Do we really want to solve it? No. We can say that, let's say capital I is equals to B sine omega t. Let's say capital I was equals to B sine omega t. So what is this formula written? This formula, if you see closely, is written as IRMS whole square. IRMS whole square is this formula written. So I can write this down as IRMS equals to root over A square plus IRMS square, which can be written as root over A square plus IRMS square from this can be written as B square by 2. So this is the formula for the IRMS when a DC current of magnitude A, DC voltage or DC current of magnitude A is superimposed over a sinusoidal current, that is B sine omega t. So this was our question number 15. Now let's move on to question number 16. Question number 16. This question is from the paper of Roorkee REE 1991. The question says that current in a circuit containing a capacitance C and a resistance R in series leads over the applied voltage of frequency omega by 2 pi by. Okay, so you have a RC circuit and you have a AC voltage, RE 91. So what you have is you have a RC circuit wherein the frequency of the AC voltage applied is frequency is omega by 2 pi. Remember, it was given in the statement that frequency is omega by 2 pi. Sometimes students get confused this with omega, but this is not really the omega, this is the f. So omega would be equals to 2 pi f, which would be omega. So okay, omega is the angular frequency. Now we know that in a RC circuit the current leads the capacitance, the current leads the voltage by an angle of phi, where phi is derived by the formula tan phi equals to xc upon r. So we can write down tan phi is equals to 1 by omega rc, and thus phi comes out to be tan inverse of 1 by omega rc. So this is the value of the angle by which the current leads the voltage in a RC circuit. So this was a pretty easy question which came in Roorkee 1991. Now let's move on to question number 17. Question number 17 says that a current of 4 ampere flows in a coil when connected to a 12 volt DC source. A current of 4 ampere flows in a coil when connected to a 12 volt DC source. Okay, so you have a coil, you have a DC source, and you had a coil means inductor. So this source had 12 volt DC source, and current I equals to 4 ampere flowed through this DC source in the coil. Now it says if the same coil is connected to volt and how many radians? It's 50 radians per second. So mind it, this is omega given, not the f. So this is omega 50 radians per second AC source. A current of 2.4 ampere flows in the circuit. It says that a current of 2.4 ampere flows in the circuit. And what does that mean? That means the RMS current in the circuit is 2.4 ampere. You have to find out the inductance of this coil. So you have to find out the L of this coil. Now the L of this coil can be pretty easily find out from this formula, because you don't need to calculate here. You can easily calculate here. It's a since you have 12 volt and 50 radians and you just have an inductor circuit, we can say that IRMS is equals to VRMS upon XL. So IRMS is given to be 2.4 ampere and VRMS is given to be 12 upon XL, omega into L. So L comes out to be 12 upon 50 into 2.4. So this comes out to be 0.1 Henry. So the inductance of the coils comes out to be 0.1 Henry. So now you will be wondering why this part of the question was given. This part of the question was given just to confuse you, because you can clearly see that if you want to calculate the inductance of this coil, you can easily find out from the AC source. This means it was given initially, means first line of the question said this. So sometimes what students do is they start finding the inductance using this, and it would be very difficult to find out the inductance by using this part of the question. Using this part of the question, you can just find the inductance in two line of calculations. So this was our question number 17. Now let's move on to question number 18. Question number 18 says that an alternating EMF of frequency, okay, this is a RE 98 paper question. Question says that an alternating EMF of frequency W is equals to 1 by 2 pi root LC is applied to a this is frequency given. So this is applied to a series LCR circuit for this frequency of the applied EMF. Okay, so this is the frequency applied. So for this frequency there were few options given. So we can see if this is the F, if I want to calculate omega, that is 2 pi F, it would come out to be 1 by root LC. So the first option says that current is at resonance and its impedance is made up only of the reactive part. Yes, this option is correct. Second option was the current in the circuit is in phase with the applied EMF and the voltage across R equals this. The current in the circuit is in phase with the applied EMF and the voltage across R equals this applied EMF potential difference. So okay, we know that current is in phase of the in phase with the potential difference, potential applied across with the applied EMF. But it says that voltage across R equals this applied EMF potential difference. Thus VR is equals to V. We know that V is equals to VR plus VL plus VC. So this is a good point of the question. When a circuit is at resonance, VL is equals to minus VC, and which we can calculate right now. We calculated VL to be inductor to be Im XL sine omega t plus phi, and for a inductor current lags and voltage leads, so this would be plus pi by 2, and VC is Im XC sine omega t plus phi minus pi by 2. So if this is plus pi by 2 plus, so this would be taken as cos, and since this is minus pi by 2 plus, so this would be taken as cos with a minus sign. Since we know that for a circuit at resonance, XL and XC are equal, so we can clearly see that VL is equals to minus VC, and thus these two things are cancelled out, and V, that is at any instance potential difference across R, is equal to the applied EMF in the circuit at resonance. So this is a pretty important, and you can see a good conclusion that came out, that is when a circuit is at resonance, you can say these three are the quantities. So let's say if here I mark 0, I say V, so here 0, I say V1. So what happens is, again here is a 0 and V. So what happens is, potential increased by capacitance is decreased by inductance, or potential decreased by capacitance is increased by resistance by an equal amount, and thus the whole applied EMF goes into the resistive part of the circuit. So the second option is correct. The third option says that EMF of the potential difference across the inductance and capacitance equals the applied EMF, which is 180 degree ahead of the phase of the current. No, sum of the potential difference across inductance and capacitance equals to 0. So option C is incorrect. The quality factor of the circuit. Okay, quality factor is a thing which is not in the course of JE, it was in the course of Rudki, but let me tell you, quality factor is Q, which is defined as XL upon R only when the circuit is at resonance. When the circuit is at resonance, quality factor is defined as XL upon R. So the question is, the quality factor of the circuit is omega L by R, or 1 by omega CR, and this is the measure of the voltage magnification. Yeah, this statement is also correct. So we got 3 correct statements. So this was our question number 18. Now let's move on to question number 19. Question number 19 is a question from JE paper of 2003. JE 2003. Question says that when an AC source of EMF E is equals to E naught sine 100t is connected across a circuit, the phase difference between the EMF in the, okay. It said that E naught sine 100t EMF, okay. It was given that, okay, this is the diagram for E, and it said that the phase difference between EMF E and the current I in the circuit is observed to be pi by 4. That is this was our I and this was our E. Now, shown in the diagram, if the circuit consists possibly only of RC, RL, okay, and the question says that the circuit only possibly contains RC, RL or LC part. So it says that find the relationship, okay, you have to calculate the value of resistance and capacitance, whatever it is. So okay, this question is a good question. Firstly, let's see if E is the EMF. We can see from the diagram that current is leading the potential difference. Leading the potential difference. And in what type of circuits current lead the potential difference? Current can lead the potential difference only in the capacitor circuits. Current can lead the potential difference only in the capacitor circuits. That means this circuit contains a capacitance. And if it contained only capacitor, then the phase difference must have been pi by 2. But since it is not pi by 2, it is pi by 4, that means there is a resistor also. So the circuit is a RC circuit. Now it is given that phase difference is pi by 4. So we know that in our RC circuits, 10 of phi is equals to XC upon R. So 10 pi by 4, which would be 1, would be XC upon R. Now 4 options were given in this question. First option was A is that resistance is 1 kilo ohm and capacitance is 10 microfarad. So is this option correct? Let's check out. We want to get XC upon R to be equals to 1. So calculate XC for this. It would be 1 by 100 into 10 and 10 to the power 6. So this would be 10 to the power 3. So XC is 10 to the power 3 and R is 1 kilo ohm. So it is 10 to the power ohm. So okay, A option is correct. What about B option? B option says that R equals to 1 kilo ohm and capacitor equals to 1 microfarad. It is not possible because R is 1 kilo ohm and C is 10 microfarad. Satisfied. So B option is incorrect. C option said R is 1 kilo ohm, L is 10 Henry. It is not possible because we just stated that the circuit is a RC circuit. And the fourth option says that R equals to 1 kilo ohm and L equals to 1 Henry, which is also not possible. So this was a question from JEE 2003, and you can see that this question was also pretty easy. So with this question, we come to an end to our module, advanced level module of alternating current. In this module, I tried to cover all the questions from different regions of alternating current, and basically not much questions or not much variety of questions can be formed from alternating current. It comes, the whole question boils down to drawing a proper phasor diagram and then writing the equations properly, and just remembering the formula and important concept that capacitor in a capacitance in capacitance current leads potential difference by pi by 2 and inductance current lags behind potential difference by an angle of pi by 2. That are the two most basic things which you must remember. With this, you can solve each and every question of alternating current from anywhere you would like. So I hope you enjoyed the lecture, and if not, if at some point you didn't understand, you can go back to that point and just revise it properly. Hope you enjoyed the lecture. Thank you very much.